Good morning, students. Welcome to the lecture class on control engineering. So, in the last session, we have discussed about some of the basics of the Bode plot. So, today we'll try to solve some of the simple problems on Bode plot. So, the statement is sketch the Bode plot for the system having g of s into h of s as 20 divided by s into 1 plus 0.1 s. So first, you need the very first step is you need to identify the factors. That is, it should be in the standard format, that is k divided by s into 1 plus ts. If it is not in this form, first you have to convert this the given transfer function into this standard time constant format. So in that, the first you need to, by comparing the given equation with this, so k will be 20, magnitude 20 log 20 will be plus 26 dB, and there is one pole at the origin, that is 1 by s, this term, and its magnitude plot is a straight line passing through the intersection points of omega equal to 1, and the magnitude value is 0 dB with minus 20 dB per decade as the slope. As I told in the previous video, so always you have to take for a simple pole or simple 0 at origin, the slope as 20. Since it is a pole, we have taken with a negative sign. Then there is a simple pole of first order, that is this term 1 plus 0.1 s. So that is for this simple pole, comparing with this standard equation. So t is 0.1 here. That means the cross over corner frequency or break frequency will be 1 by t, that is 10 radian per second. After that, you construct this table, that is in the first column it is the terms, in second column slope, third is magnitude, fourth is break frequency, and fifth one is cumulative slope. So in this, the terms are, the first one is k, that is value is 20, the second one is 1 by s, and third one is 1 divided by 1 plus 0.1 s. For this one, the slope will be 0, magnitude we have calculated it as 26 dB, there is no break frequency, and cumulative slope will be 0. Similarly, for the second term, that is 1 by s, for the simple pole at origin, the slope will be minus 20, no magnitude, and frequency will be at 1 radian per second, and the cumulative slope means this plus this will be minus 20. Then the third one is 1 divided by 1 plus 0.1 s. For this also the slope will be minus 20, there is no magnitude, the break frequency is 10, that is here we have calculated radian per second, and the cumulative slope will be this plus this will be minus 40. After that, you need to construct the phase angle table. For that, the angle will be minus tan inverse of omega by 0, that is wherever s is there in the given equation, you need to replace this by j omega. So here it is in the numerator, it is 20 plus 0 j omega. So that means the imaginary part will be 0 and real part is 20 there. So 0 by 20 will be 0 only. So we are ignoring that. And in place of s, I am substituting j into omega plus 0 is the real part there. So for that reason, I am writing here with a negative sign the denominator terms, minus tan inverse of omega by 0 minus tan inverse of 0.1 is the imaginary part and the real part is 1. And you need to select the omega values. So the first value omega is 0.1. If you substitute that, angle will be minus 90, and here it is minus 0.57, and resultant angle will be minus 90.57 degree. Similarly, vary the omega 0.1, 0.5, 1, 2, 10, and 10. Sorry, 50. So the respective resultant angles are these. After construction of this phase angle table, we will go for the construction of the Bode plot on semi-log graph sheets. Okay. So this is the construction of that given problem. So here first, as we have discussed in the last video, for magnitude plot and phase plot, it is having the two parts. Both plot is, so the above portion is, this one is magnitude plot and this one is the phase plot, and the only similar thing is for both the plots the x-axis is same because it is containing the logarithmic value of the frequencies, angular frequencies, whereas the y-axis are differs. For magnitude plot it is the magnitude values, that is dB values, and for phase angle plot these y-axis is angle values. Okay, so for the first step is, here for the scaling purpose I will mark one line as the 0 dB line, the first step. Okay, and I will take the next line as 20 dB, 40 dB, and this one is 60 dB. Like that, from here towards downside it will be minus 20, minus 40. Okay, and how to read this semilog? Here this will be 0.1, the next line will be 0.2, 0.3, so on up to 1. After that the reading will be 1, 2, 3 up to 10. After that it will be 10, 20, 30, 40, like that up to 100. So like that you have to read this graph. Okay, so in the first step, after drawing this 0 dB line, first you mark a point on this 0 dB line where omega equal to 1. Okay, so this is the origin point. From this point you need to draw the slope lines. Okay, so for the first one, here if you see here, the first, this one, so it is 0, minus 20 and minus 40 are the slopes. Okay, minus 20 means it should start from 20 and it should end at 0. Okay, so like that, first you draw a line from this point to 0, then from 40 to 0 here. Okay, then after that, so the first line will be starting from 20 and it will cross this 0 dB line at omega equal to 1, and the next frequency is 10 here, 10 radian per second. From this to 10 radian per second it will be parallel to this 40 dB line, minus 40 slope line. Okay, so from here to here it is with 20 and from here to 10 it is 40 and it will tend to infinity. Okay, so this line is without k, but here we know the value of k, so 20 log k is 26 dB. Okay, so for that, at 26 dB you draw a line with 0 slope. This is the 26 dB line. Okay, then so our slope, the plot is from starting from 20 up to omega 1 equal to 1, it is intersecting with 0 dB. After that it is a parallel to this 40 line, minus 40 line up to this omega equal to 10. So now to get the actual line, that is actual plot, so shift this point on this 26 dB line. Okay, so this is our actual plot, so you have to shift this entire plot on this 20 dB line, and while shifting all the lines with the same slope or same inclination you have to shift. So this is going to be our resultant line or resultant slope, that is which is minus 40 dB per dk. Okay, and similarly for the phase angle we have denoted this x-axis as angular frequency, logarithmic value of angular frequency. First one is, it will start from 0.1 and here it is 1 and here it is 10, and we have calculated the angles for the different values of omega, that is omega equal to 0.1, 0.5, and we have the resultant angles. So here also I am taking the scale as 1 unit equal to 35 degree, so 15 degree. Okay, so when omega equal to 1 the angle is minus 90.57, mark here. Similarly, when omega equal to say 2, the angle is 101. So your 101 will come somewhere here when it is omega equal to 2. Similarly, for all the values of omega, you mark the points, then join those points with a smooth curve. So that is going to be your resultant phase angle plot. So here remember, while constructing, first you have to draw the 0 dB line. On that line, mark a point on first frequency, that is omega equal to 1. Join from that point, draw the slope lines. The first slope is minus 20 from there. Then second slope is minus 40. After that, your line will be, that is your plot will be from minus 20 to 0 up to omega equal to 1. After that, from omega equal to 1 to 10, it will be with minus 40 slope. So this line should be parallel to this minus 40 slope. Like that, you have to draw this line. After that, to have the effect of K, we know the value of K, it is 26 dB. So shift the entire this plot on this line in such a way that it should intersect with this 26 dB line. So first you will need to shift this point here on this. Then parallelly you have to shift these lines. Okay. So this is going to be your phase, magnitude plot, and this is your angle plot. Now coming to the second problem. The statement is a unity feedback control system has G of S as 80 divided by S into S plus 2 into S plus 20. Draw the Bode plot. Determine gain margin, phase margin, gain crossover frequency and phase crossover frequency, and comment on its stability. So first step is, first you have to check whether the given transfer function is in the time constant form or not. So here the time constant form is K divided by S into 1 plus T1S plus into 1 plus T2S. So if you compare these standard form to the given form, so first we try to simplify that. So it is 80 divided by S into, here I should have 1 plus T of S. So I will take 2 as common. So it will be 1 plus S by 2. From this I will take 20 as common. So it will be 1 plus S by 20, which will be 2 into 20. So if you simplify this, you will get the equation as 2 divided by S into 1 plus 0.5 S into 1 plus 0.05 S, which is in the standard form, time constant form. Okay. After that, you need to identify the factors. So first is K value is 2 and one pole is at origin, 1 by S is at origin. Then the simple pole, that is 1 by divided by 1 plus 0.5 S with T1 as 0.5. So for that, the omega B1 will be 2 radian per second. Then one more pole is there with T2 as 0.05. For that, omega B2 will be 20 radian per second. And for this, the slope will be minus 20, and minus 20. You have to construct that table also to get the cumulative slope. After that, you need to write the phase angle table. For that, wherever S is there, replace that S by j omega. So pi is given by tan inverse of 0 by 2. So here I will enter 2 plus 0 j omega. Okay. So in that, the imaginary part will be 0. Okay. So it is 0 by 2 minus the denominator terms you have to take with negative sign while writing the angle, omega by 0 minus tan inverse of 0.5 omega divided by 1 minus tan inverse of 0.05 divided by 1. So like that, you construct this table and vary the omega value from 0.1 or 0.2 to the possible highest values, and at the end it is infinity. So here it is 0 degree, 0 divided by 2 will be 0, tan inverse of 0 is 0, and tan inverse of infinity is 90 degree. Similarly, vary the omega value and get the resultant angles. After getting these resultant angles, you have to go for the construction of the Bode plot. Okay. So here, as I said in the previous problem, first you need to draw the 0 dB line here. That is the first step. Then mark 20 plus 20 dB, 40 dB and 80 dB. Similarly, mark a point on this 0 dB line where omega equal to 1. So this is the 0 dB line. Okay. After that, to that point, you draw a line from 20 dB, 40 dB and 60 dB. Okay. And your plot will be, okay. So first, the first frequency, that is the first break frequency is 2 radian per second and the second frequency is 20 radian per second here. So your plot will be based on those values and their respective slope. So here, after drawing this 0 dB and 6 dB line and these slope lines, okay, so you try to shift this point which is at 0 dB line on this 6 dB line. So for that, you draw a line from first crossover frequency to this slope, this line. When you are drawing this line should be parallel to this minus 20 dB slope line. Okay, so that is, it is starting from here and it is ending at omega C1 equal to 2, and meanwhile it is parallel to this 20 dB line. Then the next line will be from omega C1 to omega C2, and this line should be parallel to this 40 dB per decade. That is, this should be parallel to this line. Like that, you have to draw this line. After that, it is minus 60 dB line. Okay, so this is the construction of the magnitude plot. Then you need to go for phase angle plot. So here we are having minus 180 degree as the reference line. So minus 180, I have taken 1 unit as 30 degree. So if you go in upward direction, you have to add, and if you go downward direction, you have to subtract. Okay, minus 180 plus 30 means minus 150, minus 120 and 90 degree. And here it is minus 210, minus 240 and 270 degree. So after that, you have the table, phase angle table, which contains the different values of omega and their respective resultant angles. So that is, when omega equal to 0.2, the angle is 96.27. So at omega equal to 0.2, the angle is 96. Similarly, at omega equal to 2, the angle is 140.7. So this is for omega 1, the 2 is here, so 146. Like that, for the different values of omega, you mark the angles in this phase plot. So then you join those points with a smooth curved lines. Okay, so after completion of this plot, now there is necessary to find out the gain margin value and phase margin value and the gain crossover frequency and phase crossover frequency, that is omega GC and omega PC. So here first we'll try to identify the gain margin value. So we have this phase plot here, and it is having the intersection with minus 180 degree line at this point. Okay, so from that point you draw a vertical line till this 0 dB line. Okay, and the difference between, or the distance between this 0 dB and this magnitude plot, this one, this is going to be your gain margin. This value is 21 dB. According to the respective scale only, you have to read that. So it is 21 dB in upward direction. So you have to take it as plus 21 dB. Similarly, you just check the intersection of this phase plot with the 0 dB line. So here it is having with 0 dB line. So from this, you draw a vertical line till minus 180 degree line, or till the x-axis, and the distance between this phase plot and 180 degree line will be the phase margin. So here it is 38 degree is the phase margin in this problem. After that, you need to identify the gain crossover frequency and the phase crossover frequency. Wherever this magnitude plot is having intersection with 0 dB line, from that point draw a vertical line up to this x-axis, and where exactly it is meeting with this x-axis, that value is going to be your gain crossover frequency. Similarly, the intersection of this minus 180 degree line with phase plot with 180 degree line, from that point up to this x-axis, and this value of omega will be the phase crossover frequency, that is 6.35 radian per second. And here we can say that the system is stable because the gain margin is positive. Okay, so here I have taken the scale as 1 centimeter equal to 20 dB, that is 1 unit equal to 20 dB, and 1 centimeter equal to 30 dB for this phase plot. Okay, so remember, first step is 0 dB line, then mark a point here on 0 dB. So here, after drawing that 6 dB line, and after drawing these slope lines, okay, so you shift that 20 dB line on this slope, on this 0 dB line, and this line should be with minus 20 up to the next frequency, that is omega c1 equal to 2. The slope of this line should be minus 20. Then from omega c1 to omega c2, the slope will be minus 40. So this line should be parallel to this 40 dB line, slope line. After that, it is minus 60 dB. Okay, and for this phase plot, we have the different values of omega and their respective angles. So just you need to mark those points, then you have to join those points with the smooth curve. So now, after drawing this, to identify the gain margin, first you check the phase plot, phase line or phase curve, where exactly it is having the intersection with minus 180 degree line. So here it is having the intersection. From that point, you draw a vertical line from 0 dB to this x-axis. Whatever the distance between this magnitude plot and this 0 dB line is going to be your gain margin. Similarly, check for this magnitude line having the intersection with 0 dB line. So here it is having the intersection. From this point, draw a vertical line up to this x-axis, and in that, the distance between this phase plot and this minus 180 degree line will be the phase margin, and the intersection of that line with this x-axis will gives you the gain crossover frequency, that is omega gc value. Similarly, this intersection with x-axis will gives you the value of phase crossover frequency, that is omega pc. So here the answers are omega gc is 2.1 radian per second, omega pc is 6.35 radian per second, the gain margin is plus 121 dB, phase margin is 38 degree, and the system is stable. This is the comment. So you have to write this answer after this table in the exam, because this graph will be at the beginning of your answer booklet. Okay, so on that booklet also you have to mention these answers. Along with that, after this table you have to write the answers. So if you have any doubt, you can leave the comment in the comment box. Thank you.